Now, you can have, like I mentioned earlier on, you can have third order and higher orders of reaction, but those are not as important and rarely present in the literature. Now, you can also have pseudo-zero order reactions, right? For example, with suspensions, suspensions have even solid state medicines, probably those that are hygroscopic, those that draw moisture, right? They will also act like suspensions, right? Because our suspensions are essentially solid drugs that do not, they do not dissolve in the solvents in which they are placed, or they release just very little amount of the solvent into of the substance of the drug into the solvent. An example include our mist mag, right, which is always in suspension. Even paracetamol is usually in suspension, right? So for this, your equation is similar. Your calculation will be similar to zero order reactions, except that your K will be replaced by K prime, okay? And of course, when you're talking about how suspended drugs degrade in zero order, it's basically because the rate of change of the concentration in the liquid media is not determined by the concentration of drug in that liquid media, but by how much of the concentration of the drug in the solid media moves into the liquid media, right? The important point is that the amount of the drug in the solution remains constant despite its decomposition with time. Okay, now once all the solid suspended particles have been converted into drugs in solution, system changes to a first order reaction. Okay, so that's a pseudo zero order. You can also have a pseudo first order, where a second order or bimolecular reaction is made to behave like a first order one. You can have this in the composition of ascorbic acid is vitamin C, or hydrolysis of aspirin. You know, aspirin is hygroscopic. If you put a tablet of aspirin on the table, it absorbs water. And of course, in that medium, it begins to hydrolyze, okay? Now, there are also things we call complex reactions that, you cannot really describe, by just the first order or second order, right? And the simplest case is one in which, okay, see, for example, this example that I cited here, drug A is changing into reactant B, but notice that some of the reactant B are also changing back into drug A, right? In this case, the rate at which A is changing to B is similar to the rate at which B is changing to A. It could be both of them could be zero order or first order or second order, right? But then they are similar. Now, on the other hand, you can also have you can have an opposing reaction where A is changing to B at a slower rate than how B is changing to A. And in this case, you find it very hard to identify or to find substrate B as a product, because as A is being converted to B, B is being mopped up back, to form A again, right? An example of this reaction is epimerization of tetracycline. Tetracycline, exists as epimers, right? So its change between its states are very, very rapid, right? So you have epimerization of tetracycline as an example of opposing reactions. Now, you can also have consecutive reactions. I realize our time is beginning to round up, but I'll be as fast as possible, right? For consecutive reactions, A is forming B and B is forming C, right? So if the rate at which B forms C is different from the rate at which A forms B, then you can say that B is considered an unstable intermediate and the rate determining step for overall reaction for conversion of A to C, sorry, for conversion of A to C. Okay, an example is the formation of benzophenone from chlobenzodiazepine. Benzodiazepine is it's usually classified as part of benzodiazepines, psychotics, but then because of its chain to benzophenone through an intermediate lactum form, right? Benzophenone is a more longer acting substrate from the drug, but through an unstable intermediate, right? So essentially, the use of this has been very limited to scientific research, okay, because of its passage through an unstable intermediate. Now, remember what I said. Once this rate for conversion of B to C is different from the or let's say higher to the one from A to B, then this becomes the rate limiting step. But if the conversion of A to B is faster than conversion of B to C, then the conversion of B into C will be the rate limiting step. So the slower part of the equation is usually the rate limiting step. Now, you can also have parallel reactions where A is changing into B as it is changing into C. For example, you can have insulin degrades by two mechanisms, deamidation and polymerization, right? And the relative rates, depends on both pH and temperature. So both rates of both orders of reaction are zero order, right? Depending on both the pH and the temperature at that time. Now, finally, how to determine orders of reaction. You can have there are about four main that we talked about, even though there's the Arrhenius method, which I basically left out. The Arrhenius method is a bit confusing, and then it could also overstate what you have, even though because it's mathematically intense, people tend to use it some more. I can use substitution method from data, like all of what I described were substitution methods. You just use the data you've gotten in the kinetic study, substitute it into the equation and calculate. This is definitely what you're going to be doing, as classwork, test, and exam. Now, there's also the data plotting method, which I cannot rule out, right? It's also possible that you may need to draw a graph as well, but definitely the skill for doing this, because you'll be using a log graph. I know some of you are already conversant with that from 200 level, right? But then you will be refreshed as well. So there's the data plotting method where you get your data from a kinetic study, plot into the graph, and identify both your slope and your intercepts, all of that. Next, also, you have the initial rate method, where you plot rates of reaction against concentration, and initial rate determined from the gradient at time t is 0, right? You use that to predict, depending on how the graph appears, right? You use that to predict which of the orders of reaction it is. You can also use the half-life method. Basically, half-life is proportional to that's the inverse of the initial concentration times the order of reaction, the inverse of the order of reaction. So if you have two reactions run at different initial concentrations, right, you can use this calculation, this formula to detect what order of reaction the substance follows. Now, in terms of so far, in this last 1 hour or less, we've talked about rates of reaction. And under that, we talked about the constant, which is K. We talked about orders of reaction or magnitudes of how products or substances, drugs, react to form substrates. So we talked about zero order reactions. We talked about first order reaction and second order reaction. I also mentioned that third order reactions and other higher orders are possible, but they're very rare in the literature or not as represented in the literature. Now, some of the things I want you to look at are summarized here. At zero order reactions, this was our integrated rate equation, our T-half, and of course, from the linear graph, these are the data that you can gather from both zero order reactions, first order reaction, second order reaction, where the concentration of A is equal to B, or where the concentration of A is not equal to B. Now, the first order of assignment that I have for you is that I'm going to put in this document in the classroom, in the Google Classroom. So please do the assignment. I'll post it this evening, and then you should have submitted it by tomorrow, by end of class tomorrow. It's just for you to copy what you have in the notes, right? I want to be sure that you know or you understood at least some of the things we discussed. Any questions as we round up this class? Any questions or any difficulties accessing the class, the Google class? Hello? Wuraola, are there challenges accessing?
No, sir. No, sir. No, sir.
Okay. Okay, so with that, we've come to the end of this class. It should be uploaded on your Google Classroom latest by tomorrow, latest by this evening, and then the slides as well will be posted, and the assignment will be posted this evening, and you have to turn it in by tomorrow, latest, I think 9 p.m. tomorrow. All right, in the absence of any other questions, I'll say have a good evening. Bye.
Way in which drugs move through the body, through the body system.
Excellent. So it's